Okay, so today we are going to start talking about 3.1, which is exponential functions. Exponential functions, all of you have learned about these at some point in the past, but they take the form ab to the x. The difference between a polynomial was x to a constant power. Exponentials are a constant to an exponent power. So if we look at a few different functions, we're going to classify them as exponential or not. This is example 1. So A is f of x equals 3 to the x. This is a constant to the power of x. That's an exponential. B is, oops, not B. It's supposed to be g of x. Part B is g of x equals 6x to the negative fourth. No, not a function. I probably should do something different than that. Not a function, because x is not the exponent. X is the base. H of x here is an exponent, negative 2 times 1.5 to the x. Yes, an exponential function. A in this case is negative 2. B is 1.5. This one up here, A was 1 and B was 3. Part D, 7 times 2 to the negative x. Yes, that's exponential. The exponent is a variable. Yes, it's negative x this time, but that's fine. A equals 7, B equals 2. And E, Q of x, we've jumped from K to Q. 5 times 6 to the pi. Yes, pi is a perfectly legitimate power. 6 to the pi. But no, that is not an exponential function because that exponent is not a variable. We're going to look at computing some values for an exponential function. A very basic one. This is example 2. F of x equals 2 to the x. So I'm going to do f of 4 equals 2 to the fourth. 2 to the fourth is not 2 times 4, it's 2 times 2 times 2 times 2, which is 2 times 2 is 4, times 2 is 8, times 2 is 16. F of 0, 2 to the 0. Anything to the 0 power is 1. It's really important that you know that and you keep it in your head. Anything to the 0 power is 1. That will make our default y-intercept be 1. 2 to the negative 3. Negative exponents move to the denominator, so 1 over 2 to the third, which is 1/8. 1/2. 2 to the 1/2 is the same as square root of 2. And we're going to leave it in the exact form. 2 to the negative 3/2. This one has a couple of things in it. So f of negative 3/2, 2 to the negative 3/2. First, I'm going to start with the negative part. Then I'm going to convert this to a radical one over square root of 8, which I can reduce that 1 over square root of 2, reducing my radical 4 and 2, 2 and 2. My pair of 2's goes to the outside. My individual 2 goes inside. Now I should rationalize this. Square root of 2 over 2 times square root of 2 times square root of 2 is 2. So square root of 2 over 4. So to rationalize, I multiplied by, right here, a clever name for 1 that gets rid of my radical in the denominator. Okay. Determine the formula for the exponential functions. So we've got a table here with a couple of functions. G of x and h of x. And I'm going to leave a little room here so I can do some things to show what's happening. And here are the points. These are given to me. They're shown on the graph, but they're also given in a table. So I'm going to look at what is the ratio here. I am multiplying by 3. I continue multiplying by 3. It's easier to see the multiplying by 3 further down. So writing this function, g of x, my a is my y-intercept. That's this line. 4, my b is my ratio, multiplying by 3, and there's my function. H of x looks like I'm dividing by 4, so that's multiplying by 1/4. I want to think of it as multiplying, so that's why I'm putting the fraction here. So h of x, again, y-intercept is given. Unless there is a shift, which sometimes there will be, but unless we have a shift and we move it up, down, left, right, 0 is the y-intercept, and that is a. I do regularly put parentheses around b because it just makes it cleaner. It's easier to tell, especially when it's a fraction, that the whole thing is taken to that power. So thinking of exponential functions, we have exponential growth. Looks like this. As I go left to right, I'm increasing. There's a couple of key features here. We have a horizontal asymptote. Here's the x-axis, so y equals 0. That is the default. We will move them later. But for now, the default is 0. This is growth. Growth exists when for x greater than 0. So if this is a positive x in the exponent. Actually, I shouldn't say it that way. I should say it when exponent is positive. So actually, we'll do it with positive x here. It is growth when b is greater than 1. It is decay when b is between 0 and 1. If b is 1, 1 to any power is 1. So if b is 1, that's a times 1 to the x, which is just y equals a. That's a horizontal line. If b is negative, say I have something like -2 to the x. Well, let's make an xy table. 0, 0, -2 to the 0 is 1. -2 to the 1/2 is square root of -2, which is I square root of 2. That's not going to show up on my graph. -2 to the 1 is -2. -2 to the second is +4. This is not an exponential function. It is a function with a very choppy domain because you end up with a lot of imaginary numbers in here, because the 1/4 would also be, and the 3/4 would also be imaginary. But a very choppy domain, but it is a function. But it is not an exponential function. Over here, I'm going to put y equals ab to the negative x. This is growth. B to the negative x flips my fraction, becomes a1 over b to the x. So this one is growth. You switch them. And it is decay. I guess I should show decay here when b is greater than 1. A decay function looks like this. It's reflected over the y-axis. Reflections over the x-axis can happen. We'll talk about those, but that is not exponential decay. Let's talk a little bit about function transformations. So we're going to start with this function. This is example 4. I guess that's supposed to be f of x. So we're going to do g of x, and it's going to be f of x minus 1. So whenever I put something on the inside here, that means I'm shifting it right 1. When I plug it into equation form, so this is function form, equation form. Okay, hold on. I need to do colors here. I'm gonna do this one in blue. My initial function, f of x equals 2 to the x. So if I graph that, y-intercept is 1, 1/2 here, 2, 4. Looks roughly like this. So this means I just shift every point to the right 1. I'm gonna move that over 1, move this over 1, move this over 1, move that over 1. Okay. H of x is f of negative x. That's 2 to the negative x. That means I have a reflection over the y-axis. I'm just going to take each point and reflect it across the y-axis. K of x means I take each point and I multiply it by 3. So again, I keep going back to f of x. So this 1/2 becomes 3/2. This 1 becomes 3. This 2 becomes 6. 6, 8, 9, 10, 11, 12. This 4 becomes 12. And my graph is stretched out vertically. Okay. That's some basic transformations. We are going to talk about the natural base E. e. And now I can use actual limit notation. As x approaches infinity, and we talked about e in Algebra 2, but here it is. This is approximately squiggly equal sign 2.718. So I would approach E if I did 1 plus 1 over a million to the power of 1 million. Why does it get small, approach a constant number as I'm doing this? Well, I add a little bit smaller number, but then I multiply it by more each time. So it ends up approaching this number that we call E, which is the natural base. Understanding how useful E is becomes important and really useful in calculus. But we're going to analyze this function and do a little function analysis on it. It looks like this. Looks a lot like 2 to the x. It's just a slightly different curve shape. It does go through 1, 0, or 0, 1, sorry. It has a y-intercept. Still has an x-intercept as, or asymptote on the x-axis. No x-intercept. The domain, and this is pretty much true for all exponential functions, is all real numbers. So that is negative infinity to infinity. I want domains and ranges written in this form using interval notation. The range, I'm looking at the y-coordinates. Because 0 is an asymptote, this one doesn't cross the asymptote. It is not including 0. We need to start getting the including and not including parts right as we're doing these. This is not including 0. It's continuous across its whole domain. There's no breaks, no jumps. It just is negative infinity to infinity. It is increasing from negative infinity to infinity. It is never decreasing. It does not have any symmetry. Boundedness, it is bounded below. Extrema, this has no maxes or mins. It is a smooth curve. Asymptotes, it has a horizontal one at x equals 0. End behavior. Again, for end behavior, I look at where is the graph going as it goes to its ends. And I can only do this if it's defined at its ends, but this one goes negative infinity to infinity. So we're good. As I go to this extreme left end of the graph, my y-coordinate goes to 0. As I go to the extreme right end of the graph, my y-coordinate goes to infinity. Yes, these are slightly different. So now we're going to do some transformations on e to the x instead of 2 to the x. Same idea, but f of x equals e to the x. Then we've got g of 2x, which means I'm doing a horizontal shrink. That's e to the 2x. So I'm going to start by graphing e to the x. 1 is 2.718. 2 is, looks about like that. Looks very similar to that 2 to the x. E to the x, I'm taking each x coordinate and I'm halving them. So again, it's a horizontal shrink. My graph was here, I squish it in this way. H of x, e to the negative x, or f of negative x. What does that do? Flips it across the y-axis. This could also be thought of as 1 over e to the x. Finally, k of x equals 3 e to the x. Again, stretching it out, multiplying by 3. Somewhere up here is 3 times as much. This is stretching it vertically. Okay, now time to talk about one of our other 12 basic functions. That was one of our, yeah, that is kind of exponential. It's called the logistic function. So we're not going to start with the basic logistic function. I'm going to talk with the more general. C over 1 plus ab to the x, or c over 1 plus a e to the negative kx, because we like e. E is nice, especially when you get to calculus. Feels harder at this point. C is known as the limit to growth or carrying capacity. If you've studied in bio populations, you might have heard the term carrying capacity. And that is kind of the upper limit to it. It starts growing like an exponential for a while and then starts tapering off. You see this with populations when the food supply starts to get low. Our basic logistic, and we're going to analyze this, 1 over 1 plus e to the negative x. Its graph looks like this, with this upper asymptote coming at 1, and its lower asymptote coming at 0. So domain, again, this is all reals for the domain. Range, however, is only 0 to 1. Now, when you get some of these models, yes, they can cross over. When you do populations, you go above and kind of, it'll eventually approach this upper asymptote. But with the actual function, it never goes above that upper asymptote. It's continuity, it's the whole domain. And it's increasing across the whole domain. Again, this is never decreasing. It could be reflected across the y-axis, and then you'd have decreasing, but this one is not. Symmetry, I suppose it is symmetric about this point. This was supposed to actually be on the y-axis. I just kind of missed. That should be right there. But we're just going to talk about symmetry as even, odd, or neither. So we're going to say none. Bounded. This is fully bounded. It's bounded above and below. You can either say above and below, or you can say fully bounded. Because there is a top and a bottom. Extrema was none. End behavior. I have labeled my function f of x, so I can use that. Limit as x approaches negative infinity of f of x. So as I go way this way along the graph, way to the left, my y value is going to 0. As I go way to the right along my graph, my y value is going to the other. Oh, I forgot to put asymptotes in here. It's going to the other asymptote, which is 1. So these are not the same on the logistic function. So graphing logistic functions. We're going to go look at our calculator and we're going to talk about what everything means on it. I'm looking at example 7. And I'm going to graph both of these logistic functions. Okay. 8 divided by 1 plus on my calculator, there's an e to the x button, that's second function of ln. Oops, I missed the x on this one. So it will not graph because I missed the x here. Anytime I don't, I always hit go to if I get an error. And I go find it. And I'm just going to zoom 6 because okay, so let's look at our logistic functions. I need to make my window a little bigger. My one had an upper asymptote of 20, so I'm going to set my y max to 25. Make this 2. Both of these, because of the actual function themselves, and actually let's go to the calculator. I'll just write them on the side. So my blue one here was my first one. It was 8 over 1 plus 3 times 0.7 to the x. That's my function. Due to some of these numbers, that middle point of where it kind of switches from going curving up to curving down is going to be somewhere over here. The upper asymptote is right here at 8. That's here, upper asymptote. Whatever that number is my upper asymptote. My other one y2 was 20 over 1 plus 2e to the negative 3x. Upper asymptote here is 20. And it looks like that one's point here, it's going to be halfway up at 10, so just a hair off the axis. So slightly shifted to the right. So that is a logistic function. We'll do an example of using one here coming up in just a second. And we'll come back to the calculator for that, but now we're going to do example 7. And we're going to talk about modeling San Jose's population. This is San Jose, California. And we're given these two populations. And we're told it was growing exponentially. 248 and 2000, 895. It grew like 110,000 in 10 years. That's a lot of population growth. So we're going to take essentially the form y equals ab to the x. So let the population t years after 1990. So we know the initial population. If we go this is year 0. This equals year 10. Well, I know that A is the y-intercept, so that becomes year 0. And I can use this in year 10 to find B. So 895, 193 equals my initial population, 782, 248. B times B to the 10th. That's not very neat. Let's clean that up a little bit. Two, 4, 8. This is a B, not a 6, my base. So to solve this, I'm going to initially undo my multiplication here by dividing. So I get 895,193 divided by 782,248. So I divided both sides by 782,248, and that's b to the 10th. And now I'm going to do the 10th root of both sides. 895,193 over 782,248 equals 1.0136. If I were doing this on a calculator, sometimes I think it's in the math menu on the 84. It's a lot easier with the newer ones if you want to do the 10th root. Or a lot of times I just do this as the power of 1/10, which is the same thing. To write my function or my population growth function, instead of y, we're going to call it p of t, population after t years. Well, I start with my initial population, and then I put in this b value that I just calculated, and that's to the power of t, t being the number of years. Okay. Our last one, we're going to use the calculator to solve, and it's a logistic function. You're not going to be able to solve this one by hand. Okay. It's just messy and complicated, so we're going to use the calculator. Sure, there is a way, but it's not one that I want to do. So I'm going to get rid of these graphs. And we're going to be asked here, they give us this population. Oops, that's not what I wanted. I want to start with my fraction. 31642. 1 plus, oh, 1 plus 21.602. And again, I'm going to use the e to the x button. Negative 0.50505. No, I'm recording. To the x. Okay. And we're asked, when does this population cross 1,000,000 people? We can see our upper bound is 1,300,000. I missed a number. I missed a 1. I missed a 0, actually. To add this number, I'm going to use the second INS. That's insert, allows me to add a number without having to type over everything. So insert, I went to the number where I wanted it, and I inserted the 0. I'm looking for when is it 1,000,000. So I'm going to put 1,000,000 in Y2. This is going to take me adjusting my window. Probably don't need any negatives. I probably want more than 10. Let's look at maybe 50. So I'm going to do 1/10 of that. I don't really need negatives here. I need to be more than 1,000,000. In fact, I want to be more than that 1.3 million. So I'm going to go 1.5 million, and I'll just set this as 100,000. And now I'll graph. I didn't go far enough. I guess I'm going to have to change my window. These do not intersect yet. Let's make this 200. Should grow a lot more in the next couple hundred years. Okay, now I've got an intersection. To solve this, I'm going to do second calc and go to the intersect. First curve, second curve, guess. After 84 years, the population of Dallas, this is Dallas, the population was modeled from 1900. So after 84 years, 84.5, it crossed 1,000,000. That would be the year 1985. Okay, that is the end of section 3.1.